Good morning, good afternoon, good evening to everyone. Welcome to today's session, Geospatial Data Wrangling in Python. This is the fourth part in a series of 6. In case you missed the previous ones, you can find them on the YouTube channel of T-Systems. Just let me walk you through the sessions that we already hosted very briefly. The first one was an introduction into geospatial analysis with Python for data scientists. The second session was a deep dive into Python GeoPandas built-in dependencies. The third session was on geospatial data visualization in Python. And this current session is on geospatial data wrangling in Python. This webinar series is brought to you by T-Systems. And for those of you guys who are not familiar with T-Systems, it's the enterprise customer branch of Deutsche Telekom. And Deutsche Telekom is one of the largest telecommunication companies globally. All right, so with that being said, let me switch to the notebook, which is going to be the main content of today's session. I'm using Jupyter Notebooks. For those of you guys who are not familiar with Jupyter, it's the preferred data science platform or preferred platform for data science work used by approximately 3 to 4 million data scientists globally. All right, so in this webinar, we will talk about data wrangling, which is also known as data munging. And unlike all the data sets that we have used so far in all previous webinars, whether geospatial or not, the data is almost always dirty. The process of preparing data, cleaning it, and putting it in the right form for our analysis and plotting visualizations is called data munging or data wrangling, and this is what we're going to focus on in today's webinar. Generally, data analysis involves these steps on a broader level. First of all, data requirements. What kind of data do you need? Second, data collection. You collect the data from different sources. Data cleaning and wrangling, and data visualization. So far, we focused on the last step, data visualization, because this is the outcome. We need to know what we want to have in the end to create data visualization, to produce and communicate insights that both businesses and technical users can understand. And once you can see the outcome and you know how to communicate your insights, then you can focus on the how part. And this webinar is all about the how. All right, data cleaning. Real-world data is never in the form you need it. It always has lots of errors, wrong or bad values. It has many inconsistencies, and it does not exactly give you the results that you want to produce. It is completely messy. So last few webinars, we have plotted different layers of map and different types of visualizations. And we could do that because we had clean data. Data cleaning is one step in data wrangling. And it is well-known fact that 80% of the time in a data analysis project is spent on data wrangling. So your insights are as good as your data. And if your data is dirty, then your insights will be inaccurate and can cause harm to your business. So hence, it is necessary to clean the data and remove all inconsistencies, remove all the inaccurate and incomplete data. Let's start with Global Lakes and Wetland Database from the United Nations Environment Program. Step number 1, we always import our libraries. In this case, we are only going to work with GeoPandas, and we're going to import GeoPandas as GDP. So GDP is the abbreviation for GeoPandas. You can use ABC or 123, but GDP is the common standard. All right. Then next, we're going to load the file. We have it stored locally on our desktop, and it's a shape file, as you can see here at this ending SHP. And what we're going to do in the first step, we're just going to display the first 3 rows. So using gdf.head, and now we see the first rows of that data set, right? So you can see here in this first column, there is an ID. So obviously every lake has its own ID. We have the type, it's obviously a lake, and then we have the lake's name, and so we have the names, and we have the dam name, the dam that is built close to that given lake. And as you can see here in the first two rows, we have some missing data, right? And we have some other data is missing in other columns as well, right? So I'm just going to flip through very quickly. You see here NaN, none. So it's pretty much data that is missing here. Most importantly, if you're working with geospatial data and GeoPandas, is that you need that geometry column, right? So when you're creating a GeoData frame, this column is automatically generated, and that's essentially the geodata that GeoPandas is utilizing later on for data visualization and analysis. All right, so we just printed out the first, or we displayed the first through rows of our data set. Now let's collect some information on the data set. And we can do this by using the command .info with rounded brackets. So the information that we get is the range index, and we get information on every single row, specifically how many non-nulls do we have per column, okay? So you see here that we have 3,721 entries. We have a total of 29 columns. And now if you look column by column, you see the number of non-nulls, right? So in case of that GLWD underscore ID column, we have 2,721 no nulls, which means we have not a single data missing. But when you go down, you're going to see that there's quite a lot of data missing. All right, one important thing to mention here, depending on your experience level with programming in general or Python in specific, is that if you read the first line in the output, which says 3,721 entries, 0 to 3,720, let's be clear about one thing. When it comes to software, everything starts from 0. So if we have 2 items, there will be 0 and 1. Hence, 3,721 rows of data starting from 0 and ending in 3,720. And like I said, it also has a total of 29 columns with all the column names shown. If you see closely, you will see column lake name has only 1,491 entries, while column dam name has 519, right? So we saw that previously. Same is true for many other columns. This is what we call inconsistency. Ideally, every column should have 3,721 entries, but they don't. Let's look at the head again to get clarity, right? So once again, let me just display the first 3 rows, right? We have a lot of missing data here, okay? Now, in those 3 first row, you will notice that lake name and dam name have nones. The names of dams are missing. It is missing data in general, but in programming, it's also known as missing value. So missing values are written in 4 ways. NaN with a capitalized N, small a, capitalized N, then null with capitalized letters, null in small letters, and none with a capitalized N at the beginning. For many decades, programming languages are using NaN and the 2 different versions of null as missing values. C language, for example, while none is more of a modern addition, Python, for example. We can handle missing values in a few ways. We can keep them, we can remove them, or we can replace them. When we say remove, we mean remove the rows containing missing values. Why is it useful to remove them? Think that the UN is drawing a map which tells which lake belongs to which dam. We draw a map of 3,721 lakes, but we cannot draw to which dam 3,202 lakes belong to, right? So how much accurate will that map be? Okay, let's talk about Boolean values. It's familiar for most of you guys. So just a quick refresher. Before we go on to find and remove missing values, we need to understand the concept of Boolean values, which is essentially true or false, very much like in real life, right? So if someone asks you, your weight is 60 kilogram, true or false, you can only give one answer, one way or another. So if we apply that to detecting missing values in our data set, you can use the is-null operation, and it shows you line by line, column by column, where we do have missing data, right? So whenever you see a false, in this case, that means, okay, there is data. Wherever you see a true, that means there is data missing, okay? So there is obviously a lot of data missing. But this way to looking at the data, it's just it's helpful to get a very first glance into the data set, but it's not very workable. But there are other operations we can apply. So, for example, so above we used is null, and we can also use is NA, which is very much the same. And we can apply any. And by any, we will find those columns where data is missing. So if there's one value or more missing in a column, we get a true. If those columns are complete, we'll get a false. Okay, so now we see which columns contain missing data. Okay, you can match it with info. So you can essentially see not only if data is missing, but also how many non-null values you have per column and what type of data you have in each of those columns, right? Is it an integer, an object, or a float, okay? Now, again, just seeing true false values has limitations to its usefulness. What is better is how many values are missing on each column. For that, we can use the sum operation, right? So we use isNA.sum. And that way we see the exact number of missing value per column, right? So if you take a look at, for example, lake name, you're going to see that 2,230 lake names are missing, right? Now, you can also see how many columns have missing values at all. And you do that, you again apply isNA.any.sum. And as we know from the previous view into our data set, we have a total of 29 columns, of which 19, as we can see here, have missing data, right? And then we can do as a next step, we can figure out how many values in our data set are missing. And we do that by applying isNA.sum. And the second sum gives us essentially the total number of values. So there is more than 52,000 values missing. You may be surprised at this, but then again, this is how real world data is, right? Sometimes data collection methods can't get a certain data. Sometimes creating a data set, we miss some data, and sometimes data is just corrupted. I just want you to be aware of the fact that you should expect a lot of messy data when you deal with real life data sets, and take appropriate measures to deal with it so that you don't have wrong insights. There's also a complementary operation called NotNA, which detects non-missing values. So if you apply .NotNA.sum, you're going to get the total number per column of not missing data. So in case of the type, which is lake, that's the column where the information of the type of the object is stored, we have 3,721 data, so that's all complete. But in case of lake name, we only have 1,491 lake names, and so on and so on. So you can look at the data from different angles. Show me GeoPandas, how much data is missing. Show me how much data I have at hand. And you can just kind of understand and see what type of data you have and how you can work with it. All right, so let's take a look now at removing missing values. And there are multiple ways to do so with GeoPandas. Right, so like we said earlier, we can handle missing values in a few ways. We can either keep them, we can remove them, or replace them. When we want to remove missing values, we mean removing the entire row. And how do you remove entire rows? By using Droppin A. You just drop the NAs, and what you have left now are those rows that are complete, where no data is missing. And as you can see here, the first row in our data set where no data is missing is row number 41, right? So we have a total of 7 rows out of 3,721 where we have all the data. And we can also, what we did before, we can just check how many columns are there where data is missing, and that's a total of 19 columns. Now, you see the missing values are still there, and nothing was removed, right? Before I can make you understand this, let me explain 3 most important and independent concepts in Python, which is copy of data, return value of an operation, and type of value and variable. So these concepts might be familiar to many of you, but those of you who are relatively new to Python, take this as a quick refresher. All right, copy of data. By default, GeoDataFrame operations operate only on the copy of the GeoDataFrame. It is so because Python wants you to experiment as much as you can with your geospatial data without modifying the original GeoDataFrame. Data wrangling takes 80% of any project time. Hence, we can't afford to keep on modifying the original data with irreversible operations. And that's the only reason. Now, return value of an operation. Now, a program may consist of many lines of codes, in short, LOC. By default, a program in Python is executed step by step. First LOC, and then the second LOC, and so on and so on. Python never jumps, it always does so step by step. And each LOC returns a value, which is known as its return value. The return value of an LOC is lost as soon as you move on to the next LOC. So this is exactly what happened here, right? Well, let me go back. So we dropped all the rows where we have missing data, and we see here that we have 7 rows. And then essentially what Python does, it goes back to scratch and it looks into the original data set, and still 19 columns have missing data, okay? So that's the return value of an operation. Okay. Now, okay, let's see how many values are missing in total. We did that already, so just to repeat that, we are using that operation isNA.sum.sum. So we have a total value of that LOC is 52,584. That's the number of data points that are missing in our GeoDataFrame. And a Jupyter Notebook always displays the return value, right? So what we can do, for example, we can store it in a variable and we get the exact same result, right? Like, now, numbers are not the only return values. An LOC can return a data structure too. For example, the head operation, which returns the first few rows of a GeoDataFrame, right? So we can store head in a variable as well, right? And then we get the first 3 rows when we call this variable. Okay. Now, I think we can skip that because it's very basic. So. Okay, let's go back to the GeoDataFrame. Now, getting back to our geospatial data, if you really want to modify the original GeoDataFrame, which happens to be in our case here, we can pass on an option to the Droppin A option, right? And that option is Inplace equals true. What that means is that the original data set is going to be modified, okay? So in this case, we're dropping all rows that have missing data. And we can see here in the head, bingo, we have 3 rows. Now, Inplace equals true is an option available to most, but not all of the operations. The title of the option comes from programming language jargon of keeping original in place while doing the operation. We have few other options, like we can tell GeoPandas to remove only those rows where all the values are missing. So since our original GeoDataFrame is modified and no longer has missing values, we have to reread our geospatial data set in a new GeoDataFrame. Only then we can experiment, right? So we're just creating a new variable and reading and assigning the read file to it, okay? So if we look at it, we have the original state again. We apply isNA.sum, so we're summarizing the number of all missing values, and bingo, that's the exact result, right? Okay, so drop the rows where all the elements values are missing. Okay, so we can skip this step, I think, and okay. Now let me just check. Okay, let me just check what we need to know. Maybe okay. So we still have the same number of missing values, which means there's no row where all the values are missing. So let's remove rows which have at least 2 missing values. And we can do this by applying Droppin A /2. That means drop every line where you have at least 2 missing values, Inplace true. So actually it means write that into the file. Okay, so we have 52,584. So we still have the same number of values, which means every row has only 1 missing value. Hence, we can simply use Droppin A, because by default, Droppin A is the same as Droppin A /= 1, right? That's the same. This time, let's not modify the GeoDataFrame. Let's save the return value, right? We do this by Droppin A and then apply isNA.sum, and we have 0 missing values. Droppin A operation works in 3 steps. It makes a copy of the GeoDataFrame. It removes all rows with missing values from the copy, and it returns the copy. So we saved the returned value, which is a copy, and checked it to make sure all missing values have been removed. We can also check our original GeoDataFrame to see whether it is still missing values. Okay, we look into the original file and still all the missing values are there. You can restrict the search of missing values to specific columns. Then Droppin A will remove only those rows where values are missing in these specific columns. Okay, so that's what we do here by applying. In this case, we're looking at the tail, which is the last 5 rows of our data set. This is kind of the complementary operation to head. We have head and tail. Each of them displays the first 5 or the last 5 respectively rows in our data set. So row number 3718 is missing value use column. So all other rows have missing values in columns other than use 1. So let's restrict our search. Let's look into this column. Use 1, we see here that, okay, we are having data here. Having data here, but here we have missing value in the use 1 column. So we want to eliminate that specific row. How do we do that? We do that by using the Droppin A equals subset and then use 1. And that way we are eliminating that row where this data is missing, okay? So as we can see here, now we have only the rows where in the use 1 column, the data is available and there are no missing values. By default, all operations work on rows, but for some operations, there is an option available to make them operate on columns instead of rows. So let's do that. Now, the way we do that is essentially by using Droppin A, and we then specifically tell that we should apply Droppin A to columns. Now, what we see here are only the columns where we have no missing values. And as you can see here, out of the 29 columns, we only have 10 where we have no missing values. Now let's take a look at how we replace missing values. In some cases, it's not really a good idea to remove the rows with missing values, but it makes more sense to replace the values, okay? So how do we do that? We can do this by using the FillNa operation, and you can essentially fill whatever data you wish. So let's say you want to have a 0 instead of a null or none or NaN. So this is what we do, and let's see how that looks. So we have the dam name. So we know that the first two dam names are missing. So we can replace that with, for example, a 0. Likewise, we can, for example, replace it with a string. So we can replace it, for example, with no value here. And then by using Inplace equals true, we are actually going to write that into the file. All right, so this was kind of a very short overview over how you can munch data in Python using GeoPandas. And we're going to host another webinar in exactly 1 week. And the contents of the next webinar, we will learn how to remove duplicates in data sets, how to filter data according to our needs, how to work within a subset of data inside a data set, how to index and select data, and other operations related to the data wrangling. All right, so for all of you guys who have joined us later today, this session is going to be recorded, and you will get a notification early next week with the recording. And in case you have any questions, feel free to ask them right now. In case you will have questions later on, you can still ping me via email. And I'm hoping to see all of you guys next week, same time, same place, Thursday, 6 p.m. Central Time, 5 p.m. Central European Time. And well, again, thank you again for joining us today. Have a great day and have fun with Python GeoPandas.